Hey everybody, today we're going to be taking a look at microscopy, and you might have heard that higher numerical aperture objectives lead to a higher maximum resolution. But what is numerical aperture, and what does it have to do with resolution? Well, in this video, that's what we're going to take a look at. So let's open any system here. We'll just go for a Cook triplet.
Go over to the Education tab and open up the AB theory window, which is the theory that describes how numerical aperture has to do with resolution and diffraction. So we're greeted here with a microscope objective, the image that you'd see through it, and you have the sample down there. And you might notice that there's a cone of light here. Now, the sample is emitting light in all directions, or it's, scattering light in all directions. You'll have some light going over here, some over here, but only the light in this cone is actually being taken in by the microscope. Light out here just misses. If we slide the slider over here, you'll notice that as we make the microscope objective wider, we're collecting a wider cone of light. And also, if we bring it closer to the sample, we also collect a wider cone of light, whereas we can undo that by moving it farther or making it narrower. Now, you might notice something interesting happening over here. As we make that cone of light narrower, we have a worse image. And as we make it wider, we get a higher resolution. So you could see with the loop that we have over here, it's like okay at this numerical resolution. But as we increase it way more, we get a crisper image. So numerical aperture is basically just a measure of how wide this cone of light is. But what does it actually have to do with resolution? That's what we're going to be taking a look at in the rest of this video. So we're going to start out by we're going to take this 2D problem and make it into 1D. So we're just going to take a column of pixels right through the middle of here, and we're going to arrange that over here just as a line. And that'll just make everything simpler. We can just work with a 1D line of pixels, or a 1D image, if you will, instead of a 2D image. And first, we'll plot the brightness of this 1D image as a function of the x position, or the distance along this axis. And you can see that in the whiter regions, it's brighter, the value is higher, and in darker regions like this, it's lower. Now, this is important because of Fourier theory, which says that any function, such as this one, can be represented as an infinite sum of sine waves, which means that you'll take one sine wave of frequency 0, one of frequency 1, one of frequency 2, and if you stack all those on top of each other, and you have each one with a certain offset and a certain strength, you're able to reconstruct any waveform, including this one. So let's take a look at what that looks like. So we'll add one sine wave with frequency 0, and we have this. Doesn't look too close, obviously, but let's add another one. This one has frequency 1, this one has frequency 2, frequency 3, and I made these buttons to go a little faster, so this one will add 10, and we could add another 10, and you can see as we add more sine waves, we're able to get a more complicated function. And if we add 100, we're adding this really complex sine wave, and you can see that it starts to look like this original image that we had here. And as we add another 100, it gets even better. And this is only 200 sine waves. If we added infinite sine waves, we would basically be able to reconstruct this perfectly. So next, let's go back to our original 1D image. And you could do the exact same thing with this image, because all we did before is represent brightness with, like a graph to make it look like a function. But we can do the exact same thing, but instead of adding sine waves, we add the image form of sine wave, which would look like, well, the flat line would look like this. But the frequency 1 sine wave looks like this. It's dark, it gets bright, it gets dark. And the frequency 2 sine wave looks like this, bright, dark, bright. And frequency 3 sine wave. And again, this is the exact same sine wave that we were seeing in the previous slide, except represented as an image. So a high point on the sine wave is represented as white, and a low point on the sine wave is represented as dark. And you'll see the exact same thing. As we add more of these sine waves represented as an image, you can start to see this image down here take shape. And you already see that this kind of dark region here is shown here. And if we add 100 like this, we start to see, wow, that starts to look like the original one. And if we add a bunch more, all the way up to 200, we start to see a pretty close approximation. And again, as we add infinite numbers of these, we will eventually reach the true image. And over here, this is a frequency 199 sine wave represented as an image. So again, a sine wave would look like high, low, and here it's bright, dark, bright, dark. And it goes all the way like that. And again, as we add infinite numbers of these, we will approach the original image. Now, why does this matter? Well, it makes it easier to picture why numerical aperture has to do with resolution if, instead of thinking of this image as the image itself, we think of it as a stack of these sine waves. And there are real objects called diffraction gratings that look like this. They have bright spots here and dark spots here, or spots that are transparent here and spots that are opaque here. And basically, if we stacked these diffraction gratings, which look like this, on top of each other, and we have each one with the right kind of opacity and with the right offset, if we stack enough of those, we can reach this exact original image. And in case you're wondering, because Maxwell's equations are linear partial differential equations, that means that the light field that comes off of a stack of gratings like this, so this lower, higher frequency, and this is just the rest of them, the light wave that would come off of a stack of these diffraction gratings, or the field of light, will be the exact same field of light that comes off of the original one. And that will make understanding this easier. So basically, until the end of the video, you can picture this instead as just a stack of diffraction gratings with different frequencies and different offsets. Offsets being like, how far shifted this way it is. So let's take a quick detour and look at a property of a grating, which is pretty interesting. And that is that a grating will emit information at an angle. Now, if I shine light through this grating, some of the light will go straight through, but some of the light is going to be diffracted off at an angle. Now, if we only are looking at a big enough area here to see the straight beam of light, we won't even know that the diffraction grating is there. Because if we just have, the light coming straight through, that's the same thing that we would see if the diffraction grating wasn't there. We only start to see information about the diffraction grating when we look at a wide enough area to see this first order diffracted ray of light. Because only now does it actually look different because the diffraction grating's here than it would look if we were just shining the light straight through. And this is interesting because as we have a diffraction grating with a higher frequency, it emits light at a higher frequency, which means that high frequency diffraction gratings, you need to look at a wider angle to actually notice that the diffraction grating is here. Again, if I was looking through just this area here, I wouldn't know that this diffraction grating is here because I would only see the light coming straight through, which tells me nothing about the actual diffraction grating. But if we had a lower frequency diffraction grating, if I was looking through that same area, I would know that this diffraction grating is here because it's emitting diffracted light over here, which gives information about this diffraction grating. Now, another quick detour, you might be wondering, why does a higher frequency diffraction grating actually emit light at a higher angle? Now, we can look at this through two different approaches, a path difference approach and a Huygens approach. We'll do both. So let's open path difference here. So here we see two light waves coming out of the diffraction grating at two bright spots. And you'll notice something special about light coming out at this angle specifically. And that is that if we're lining up our view of the light rays here, the extra distance that this one travels happens to be exactly one wavelength, which means that the wavelengths have the exact same phase or the same kind of position on the sine wave at each point. And that means that when this one's high, this one's high. And when this one's low, this one's low. And that means that the strength of the light will basically add together and give a really bright spot on whatever we put behind this diffraction grating. Whereas if we have a different angle, like this, for example, a bright spot here doesn't necessarily correspond to a bright spot here. And that means that you're not going to have an especially bright spot. It's only at that specific angle here that they constructively interfere and give a bright spot. And as you'll see here, if we increase the angle, it increases as we increase the frequency, it increases the angle at which that special relationship where the distance here kind of lines these up. At a higher frequency, the angle at which that will happen is going to be higher. So that's one way that we could look at it. Another way, which might be more intuitive, is the Huygens approach. And that basically says that as we shine light through the back of this diffraction grating, it will look as if light was being emitted from each one of these bright spots independently. So if we look at a semicircle of light coming out of each one of these, so this one and this one, you'll notice that at certain points, like here, the semicircles actually kind of overlap. And that is another way to see where the bright spot is. And as you can see here, the light ray coming straight through is seen here by intersections here, here, and here. And also, they intersect over here at a certain angle. And as we increase the frequency, that angle at which they intersect increases. And as you'll notice, that is the exact same angle that the path lengths match up, because this is the same phenomenon that we're looking at, just through two different lenses, if you will. So the main takeaway from this is that higher spatial frequency gratings are going to emit light at a higher angle. And that's important because if we're looking at a certain angle, we'll only be able to see diffraction gratings whose information is accessible at that angle. Suppose we're looking at this angle. We'll only be able to see the diffraction gratings who emit information at that angle or less. And that means that we'll only see coarse gratings, and the higher angle we look at, the higher angle diffraction gratings we get to. Now, remember how we were building up that original image with a bunch of diffraction gratings or a bunch of sine waves? And as we added higher and higher spatial frequencies, we started to get better and better images. Well, let's look at that again in this next slide here. So if we only collect light up to a half angle, which is half the angle of the cone of light, if we only collect light up to a half angle of 7 degrees, we only collect the spatial frequencies up to the one that is emitting light at 7 degrees. And of course, all the coarser ones too, because they emit light at even lower angles. So at 7 degrees, we get this kind of reconstruction. And that's basically cutting out all the spatial frequencies that are emitting light at higher angles, because those look invisible to us if we only look at an angle of 7 degrees. But as we increase the angle, we start to capture the diffraction gratings, the finer ones, that are emitting information at higher angles. And as we increase it more and more, we start to capture more and more diffraction gratings, and we start to get a better and better image until eventually we get an image that's so good, it looks just like the original. So let's look at the same kind of concept, but back in a microscope form. So down here, you have your sample, and up here, you have your microscope objective. And again, as we capture a small angle of light, only the diffraction gratings components that are emitting light at a low angle, or that are capable of giving their information at a low angle, those are going to be the coarse ones, the low frequency ones. And putting those together, you get a kind of blurry image. Because remember, we have to add more and more diffraction gratings to get a better and better image. And we'll only capture information from those gratings as we increase the half angle of light. And again, we could do that by making the objective wider or by bringing it closer to the lens or to the object. So as we have a higher numerical aperture, we get a higher resolution. So let's bring this back up into 2D. So we'll take that vertical column of pixels and we'll bring that back into a full image as we go to our micro view. There it is. And it's the same exact concept. The math is just more complicated because it's in 2D. But as you take in light from a small angle, you get a blurry picture because only low spatial frequencies, only those first diffraction gratings, are actually getting captured by the objective. But as we increase the cone of light, the width of the cone of light, more and more, we capture the finer and finer diffraction gratings and we get finer and finer detail. And again, you can see that through the loop here. As you have a low numerical aperture, it looks a bit blurry. And as you really crank up your numerical aperture, you can see it looks a lot sharper. And you'll notice if you look at microscope objectives, the high numerical aperture ones often are going to be a lot closer to the objective, and that gives them the chance to capture a really high angle of light. Whereas a low numerical aperture lens, like a low magnification one where you just don't need that level of detail, that might be farther away from the lens because, well, you don't have to capture so much light because you're just not going to get much detail out of that anyways. It's a low magnification objective. So hopefully that clears some things up as to what numerical aperture actually has to do with resolution. And thanks for watching. And if you want to access this kind of interactive slideshow, or if you just want a great lens design software or an optical design software, head over to trefoila.com and you can access it for free because it's still in beta mode. And once it's out, it'll be $49 a month and you could use it on the browser or you could download it. So thanks for watching and I'll see you in the next video.